Let's come back to the inverter. The inverter circuit is often represented by this symbol in the electronic circuits. The other parts are same. You should pay attention to this symbol. In digital electronic circuit, we often use this symbol to represent the connection to the high level or the power source. For this circuit, we can use familiar analog circuit to be its analogy. For example, it can be an analogy of such a circuit. Used here is the analogy of this source. Its high-level terminal or positive terminal is connected to RL. Then RL is an analogy of this bulb. And a MOSFET is an analogy of this switch. Since we've discussed that the MOSFET is a non-ideal electronic switch in fact, and ground here corresponds to the ground potential in this circuit. Okay, now the output U out is actually measuring the voltage across the switch. When the switch is turned off, the measured voltage is the source voltage. It's logic 1. The switch is turned off means the input U in is with logic 0. Conversely, when the switch is turned on, or in other words the MOSFET is turned on, the measured voltage, which is corresponding to U out, is 0. Such analogy is very helpful to the coming analysis of NAND and NOR logic gates. Now let's think about how to form the buffer after learning the inverter formed by the MOSFET. The buffer's logic is that if the input A and output is Y, A equals Y. It's a little similar with the follower formed by the op-amp. From the point of view of their logic expressions, the buffer's input and output had no differences. But it has important applications in the digital circuit. You will learn it in the following digital electronic circuit course. The second basic logic gate is the NAND gate formed by the MOSFET. That is a NAND gate symbol. If its inputs are A and B, the output is Y. Its logic expression is Y equals A and B not. According to the previous lecture, the NAND gate's logic has two parts. Only when both A and B are 1, the output Y is 0. Otherwise, the output Y is 1. Similar to what we do with the inverter by analogy, we also have an analog circuit here. Let's think about it. The two MOSFETs controlled by A and B can be considered as two analog switches. Then, what's the connection of the two analog switches should be to ensure only when both of them are turned on, the output is 0, otherwise Y is 1. In the logic expression, if both A and B are 1, which means two MOSFETs are both turned on, and the corresponding switches are both turned on, you must have got it. Only these two switches connected in series can realize the function. In other words, only when both A and B are turned on, Y is connected to the ground and the output is 0. If any one of these switches is turned off, the output is connected to the high level and equals 1. Replace the analog switches with the MOSFETs, then we get this circuit, which realizes the logic of the NAND. Only when both A and B are 1, that is, the two MOSFETs are turned on. Both. Y will be 0 possibly. Y possibly, in this circuit, UDS equals 2 times R on over 2 times R on plus RL times US. Only when RL is far greater than R on, the logic is correct. Please think about how to form the AND gate. Based on the NAND gate and their inverter, it's simple to realize the logic of the AND. The third basic logic gate is the NOR gate formed by the MOSFET. This is a NOR gate symbol. If its inputs are A and B, the output is Y. Its logic expression is Y equals A and B naught. Its logic is that only when both A and B are 0, Y will be 1. Otherwise, Y will be 0. Use the above analog circuit for analogy. Two switches controlled by input A and B are in a box. A and B are both 0 means the two switches are both turned off. Only when the two switches are turned off, Y will be 1. That is, Y will be connected to the high level. Otherwise, Y is 0, that is, Y is connected to the ground. What connection should the two switches be? It's obviously a parallel connection. Only when A and B are both turned off, Y will be connected to the high level. If any one of them is turned on, Y will be connected to the ground through it, its low level. Replace the two analog switches with a MOSFET controlled by A and B, then we get this circuit, which realizes the logic of the NOR. You can see, only when both A and B are 0, that is, the two MOSFETs are both turned off, the output UDS equals 1, since there's no path for the current to flow. If any A and B is 1, the corresponding MOSFET will be turned on and acts as a resistor. For example, the MOSFET controlled by A is turned on. UDS is the divided voltage across R on. Similarly, if RL is far larger than R on, this circuit will realize the logic of the NOR. So how to form the OR gate? Based on previous knowledge, it's no doubt that we can realize this logic.